So I've been somewhat of a recluse now for a number of years. I've made this decision in order to devote my few remaining years to research. However, I've become increasingly concerned about the number of charlatans gaining some following in the environmental debate. And I feel we need to focus on what is real, what is misleading, and what is being done to save us from ourselves. As you well know, utilising nature's energy resources is fundamental to our quality of life. And now, with over 6 billion people, that insatiable demand to release the potential energy trapped inside the carbon prison may be the catalyst to destroy all creatures on this planet. I'm sure there is not one educated person here, no matter which side of the fence you may lean on, who would dispute that we need to utilise nature's gifts more sustainably. Before we can tackle this problem, we need to resolve three important questions. The first question is the use of hydrocarbon fuels creating a problem for our future? And I will show that that is true. Then the second question is, do we have any proven technology as a viable alternative? If we do, which I intend to prove we do, then the third question is, do we have the political and corporate will to face this challenge head-on, whilst we still can? This third question, in my opinion, is the real issue. This talk is divided into three parts. First, we need to identify the problem, then second, search for the cause, and then finally seek a solution if possible. What we have here on the board is a collage of problems facing the human race that we certainly can do something about. These issues are so important that we need to identify them individually.
Over the last century, we've gone from the horse and buggy to a world teeming with hundreds of millions of automobiles. From the Model T to the latest race cars, one thing remains the same: the internal combustion engine. In these engines, a fine mist of gasoline is sprayed into the piston chamber. When a spark is added, the mixture of air and fuel explodes, driving the piston down and spinning the crankshaft. As the piston moves back up, it pushes the remnants of the explosion out of the piston, and the cycle repeats. Take the unburned fuel and carbon monoxide in that exhaust, multiply it by the number of cars on the roads, and you can see why the automobile is considered such a serious threat to the environment.
Of all the problems faced by humanity, overpopulation is the most far-reaching. The environment is under constant siege by the demand for energy and resources, and where to put our discarded waste is a growing problem. Human overpopulation magnifies these environmental problems. Humans crowd each other in cities and overburden the natural systems on which all life depends. How many children will there be tomorrow, and what will they inherit? Since time beyond memory, humans have altered the earth, hunting animals and collecting plants for food and materials, burning fuel, clearing the land, changing the course of streams, dumping waste, and introducing other species to new places. Today, these practices represent the collective activity of a staggering 6 billion people. Is it any wonder that species and habitats all over the planet are disappearing? The world's wetlands are in danger. People ditch them, drain them, dike them, dump waste in them, and drown them behind dams. Swamps, bogs, and marshes are lost to create land to farm or build upon. As a consequence, the world is losing its natural water filters, its buffers against floods and erosion, and the critical habitats and nurseries for a myriad of species.
Some of the major human activities that have contributed to the problem we now face. My answer to question one is a resounding yes. What we are doing is definitely a problem, but it's not yet too late. In regard to question two, I think we do have commercially ready alternatives to replace coal, plus other systems that may supplement our needs without using petrol or nuclear reactors. My purpose here today is to review those viable alternatives in brief. Later in the year I will move on to talk about wind power, both dynamic and solid state systems, and I will reveal the secrets of Henry Murray as the ultimate free energy system which is not yet part of the alternative energy mix. We all like the good life, so some of us look at this issue without any enthusiasm for change. My real fear is that we will only consider this problem seriously when it is too late. The reality is we could have this entire thing up and running in just a few years if we used all our resources to make the change to renewables. But we need to make that psychological shift instead of playing Russian roulette with the future of the human race. I'm not asking you to blindly accept my word that blames anthropogenic interaction as a primary cause of the current situation, or for that matter any other controversial issue regarding the environment. What I am asking is for you to look at the scientifically proven facts and then to make up your own mind based on these facts and not on fiction. This graph gives you 3 hypothetical scenarios and 2 factual records. As you can see, the model is getting much better at short-term forecasts. The original scenario in A, in green, is way off the mark, but Model C in purple, introduced in 1980, is much more accurate. The black trace records all data, including the oceans, and is right up to date, whilst the red trace is taken from the land-based weather stations. Clearly the world's temperature has risen over ½ degree globally and almost 1 degree over land since 1958, although it's not the first time it's done that. But we have to determine if this is a result of human interaction or other causes. There are about 30 greenhouse gases that absorb various wavelengths emitted by the sun. The most important are water vapour, which accounts for about 60 to 70% of the greenhouse effect. Carbon dioxide is next, which has increased 40% since 1750. Methane doubles since 1750 and at 20 times more deadly than CO2 at blocking infrared radiation. Nitrous oxide, 70% increase since 1750. And 300 times more potent than CO2. It has a half-life of hundreds of years in the atmosphere. And last is fluorinated compounds such as CFC and HFCs. And these are man-made and have been around since 1928. Ultraviolet radiation breaks down these CFCs, releasing the chlorine as a base in the upper atmosphere, which in turn attacks the ozone. Just one chlorine molecule can destroy millions of ozone molecules. In 1992, the Montreal Protocol banned CFCs. It was a good thing we didn't use bromine instead of chlorine, for if we used that as a base, you could have said goodbye to the human race, because it is 45 times more effective at destroying ozone than chlorine. Without that ozone, there would have been nothing to shield the Earth from the ultraviolet radiation. There is, however, a new threat, and that's trifluoromethyl sulfur pentafluoride, or TSP for short. It is believed to be 10,000 times more potent than CO2 and is gradually increasing since first detected in the year 2000. But unfortunately, we don't know what causes it yet, so we can't do anything about it. What we have here on the right-hand side, as you can see, the most abundant greenhouse here is CO2, which is about 57% due to fossil fuels, 17% due to deforestation and decay of biomass, etc., and 3% of carbon dioxide for all other events. Methane, as you can see, is about 14% of greenhouse gas, with nitrous oxide at about 8%, and this little stream here is fluorinated compounds. The guilty culprits for this are, of course, China, and that's increasing, by the way, and USA at 19% and decreasing, the Euro at 13% and decreasing, and the one to watch is India. This should also include Vietnam, should also include probably Cambodia, and maybe even Burma, because that's where all the corporations will go for their cheap labour in the future. The atmospheric reservoirs of carbon dioxide is dominated by the much larger oceanic reservoir of bicarbonate and carbonate ions, and by the reservoirs of carbon in limestone rocks, consisting largely of calcium carbonate shells of marine organisms. Limestone rocks alone contain the equivalent of some 20 atmospheres of carbon dioxide. In addition to that are huge deposits of clathrates on the seabed consisting of frozen methane. The amount of carbon dioxide in the air, like that of water vapour, is therefore set by the rate of equilibrium reactions linking the atmospheric reservoir to the surface reservoirs. The worst case scenario is if the equilibrium gets too far out of whack, then the Earth will find a new equilibrium state. The outcome is uncertain, but either way it could be devastating. Neither hypercold nor searing heat will suit human habitation. During this period of thermodynamic formal turnover, the Earth will be subject to violent extremes that would make much of the planet uninhabitable, and not too far away either. So that's north of the Tropic of Capricorn and south of the Tropic of Cancer will be hit worse with this. So you better go up to Siberia and live, and maybe North Canada, because there's not much land on this side of the globe. So if we study these two temperature graphs, we can see that between 1880 and 2013, the land temperature rose by 1.5 degrees Celsius, whilst the global temperature rose by 1 degree Celsius, with most of that increase in the last 50 years we saw in the last graph. Svante Arrhenius, back in 1896, said that if we double CO2 in the atmosphere, then we'll increase the average temperature of the globe by 4 to 6 degrees Celsius. The International Panel on Climate Change, which is IPCC, was formed in 1988 to collate and calibrate environmental data from across the world and prepare a report for the United Nations every 5 years on the state of the world's climate. The IPCC first forecast was for an increase of 1 to 3 degrees Celsius by 2100. But in 2001 they shocked the world by doubling this prediction. Incidentally, if there was no greenhouse gases, the planet would be 33 degrees cooler and we wouldn't be sitting here tonight listening to me. For those enlightened people who think that atmospheric methane and carbon dioxide has nothing to do with terraforming the Earth's environment, then open your eyes and look at 500,000 years of the Earth's environmental record. Over here on the left-hand side we have methane at parts per billion, and 1,000 times bigger over this side we have carbon dioxide in parts per million, and matching that is the variation in temperature over the same period. Not quite 500,000 years to be exact, it's about 430,000 years that the Vladivostok drilling's finished. So both the methane and the carbon events mainly precede temperature rises. So the CO2 concentration of 300 parts per million has not been exceeded during the last 4 million years, according to archaeological records. The current rate of increase that started 18,000 years ago, and that's just about here, the current rate of increase that started 18,000 years ago and led to the Holocene, which was 10,000 years ago, and is unprecedented in all recorded history. If anybody would like to get a copy of that chart or any of the other things I present tonight, if you send an email to the website, the association website, I'm quite happy to provide any data that you may be interested in. But you can't see that too well down on the methane side. But the main thing there is to show you the pattern. All these patterns follow each other exactly. This one, and this one, almost identical. Not quite, because there's some variation that happens between them. Right, so what we're going to look at now is an overlay of that. So that makes it a bit easier to follow. So you can see in every particular case here that the carbon dioxide aligns up with the temperature. So the temperature there you can see is in blue, carbon dioxide in red, lines up again. lines up again, and here it's shot wide off the chart, and the temperature's a little bit lagging behind at this stage, and that's over the last 18,000 years, of course. So temperature is tenuous at best and follows a positive reinforcement pattern. In other words, when it starts to climb, it even climbs more, and it climbs back on its own back, and therefore it's a positive reinforcement. CO2, on the other hand, is a direct result of events on Earth and tends to be dampened by the surface reservoirs, making it graphically more stable than the corresponding temperature variations that you see. So you can see that sort of shooting off effect that the temperature does every time the carbon gets up on the higher points. So we can look at this M bit 2, and I'll click here and there you can see it. So as you can see, for the last 18,000 years, again, as the carbon dioxide goes up, so does the temperature, almost exactly in proportion to it. We can even, and if you look at the N bit 2 here on the bottom one, you can see that even the carbon shot up on the end of this one over the last 18,000 years. And we can actually look at that too, and I've included that. As I said, I'm not going to hide anything from you. There you can see also that as the carbon goes up, so does the temperature, which is just following it a little bit behind. It's just a bit dragging behind because the carbon's gone so up in such a hurry that the temperature hasn't had a chance to catch up properly yet. And we can look at this little bit here over the last 50 years as an overlay as well. And we can't go much closer than that. And you can see here all the variations of the seasons in each particular year as far as the temperature is concerned. But as you see, the carbon dioxide is mainly consistent right throughout. So we can use that as a gauge. We can use that as a meter to tell us what the temperature is liable to be in the future. And we don't need any of these fancy modelling ideas that cost millions of dollars. We can do it right here in a few seconds. And you can see what will happen in the future. Lastly, I'll prove that right back to 5.5 million years ago, which is as far back as our accurate records can show. They don't even bother now showing you a separate graph. On this side of the graph you can see that this is carbon. They're using a single plot to represent both. They're so closely linked. Both the carbon content and the temperature are coincident and concurrent, but at different scales. So over here we have the temperature, over here we have the carbon. Some interesting results here. You can see that about 3.5 million years ago the temperature is about the same as it was now. And then something happened. You saw this little spike going down here that sort of changed everything. Then it dived down into the ice ages. So 3.5 million years ago we dived down to the ice ages. And we've been up and down like a yo-yo ever since till 18,000 years ago. Is there anybody here who still disbelieves that carbon doesn't match that of temperature? I've gone back 5.5 million years for you. And it's absolutely accurately follows carbon. So we can use carbon. Why not use it? I don't care what causes it. All I'm saying is the temperature matches it every time. So if we go back into the next graph, and we'll come back a bit, we'll talk about Milankovitch. Anybody here doesn't know who Milutin Milankovitch is? A few people. Milankovitch was born in 1879 and died in 1958. And the early part of the 1900s he was imprisoned in Serbia as a prisoner of war because he was fighting on the wrong side. And he didn't want to sit there in prison twiddling his fingers, so he decided to do something constructive. So he studied the Earth's rotational geometry in space and directly linked its movements to the climate cycles we experience here on Earth. According to Milankovitch, there are 4 primary cycle movements to which the Earth conforms, which has been remarkably consistent, as we saw in the last graph, for 1.6 million years ago. First one's obvious. It rotates on its axis approximately every 24 hours. Clearly, if the Earth is in darkness for more than 4 months, as it is at the poles, then it will freeze over, and the whole Earth would be frozen if we were in the darkness for any short period of time. Second, the Earth's axis is not perpendicular to the Sun, but it rotates around it with a tilt from the vertical at a variable angle of 21.5 degrees, with a bit of a tilt, as you can see down the bottom right-hand corner there, to an angle of 24.5 degrees, it's actually 24.4, but we won't quibble over 0.1, and completes one cycle every 41,000 years. Obviously, the most erratic weather occurs when this tilt is at its extreme angle. At present, that angle of declination is 23.27 degrees and is decreasing, which means its effect is minimal compared to 12,000 years ago, and that's one of the reasons we've had such a good time for the last 12,000 years, or 10,000 of it anyhow. Third is the wobble of the Earth around its axis, which takes 24,000 years to complete just one cycle. This has a very little effect on the weather by itself, but means that the northern hemisphere faces the sun when the sun is closest to the Earth for around about 12,000 years, and the southern hemisphere faces the sun at the perihelion during the other 12,000 years. Fourth is the concern with the orbit of the Earth around the sun, which changes from nearly a perfect circle at 93 million miles, and you can work that out in metric if you want, to an ellipse extending 94 million miles during the aphelion, and takes 93,408 years to complete one cycle. This has a profound effect on the weather patterns, with the Earth a further million miles from the sun at the aphelion. It is even worse when all three long-term cycles combine together at their extremes, which will last for more than 1,000 years when this happens. Unless CO2 levels are extremely high, then the Earth will suffer a very long ice age during this period. At present, we are halfway from this extreme, being 93,500 miles away from the sun. We're supposed to be getting colder because we're moving further and further away from the sun in the winter. The tilt down the bottom here is halfway, as you can see by the solid line up there. And we're moving further and further to be parallel more or less with that axis, at least 21.5 degrees. So likewise, we should be getting a little bit warmer than we are, where the sun is reaching both the northern hemisphere and the southern hemisphere for most of its cycle, which it doesn't do at the extreme so well. At the moment we're facing Polaris, that's our North Star, and in approximately 15,000 years' time we'll be facing Vega over here, from this top one over here. This has really nothing to do with our conversation, except for to show you that all of these are having absolutely minimum effect on our weather at the present time, and hasn't done so for at least 12,000 years, and won't do so for another 12,000 years to come. I also might mention to you that if we change the intensity of the sun, the radiation from the sun, by just 1%, 1 part in 100, then the temperature on Earth will change by 50 degrees. And we certainly wouldn't be able to live here, because that means at the top temperature the water will be boiling, and at the bottom part it'll be so damn cold it's near zero. So certainly we're very, very lucky that we're 93 million miles away from the sun, and we almost stick there for most of the time, because we were just 1.5 million miles further away in either direction. We'd either be boiling or we'd be freezing. So we need to be exactly on that circular orbit from Earth. So we're very tenuous in the position we are, and we're so damn lucky, because otherwise we wouldn't have water that can freeze, water that is water, and water that can vaporise up the top, all in the same span. Just that span where we're living at the present time. Anywhere else, it'd be too damn hot or too damn cold. Right, let's see where we can sum up what we're at the moment. Short-term effects on the Earth climate are normally the result of sunbursts, generally every 7 or 11 years. Volcanic and other seismic activity can also trigger short-term climate changes that may last 2 or 3 years at the most. The normal long-term orbital variations has little or no effect on our climate, certainly not in the last 200 years, and certainly not in the next 200 years. Absolutely no effect on our climate whatsoever, as I showed you from the graph. Realistically, we are only concerned with the next 100 years. Beyond that, I don't think there's anything to worry about. Third, the only thing that has changed in the last 200 years, and what is that? What is the only thing that's changed in the last 200 years? Carbon. The content of carbon in the atmosphere is the only thing that's changed in the last 200 years. And that's a massive increase of that atmospheric carbon. Its content, and all the other greenhouse gases that go with it. As we have seen, the carbon content increases, so does the average global temperature. So close is this nexus that we can use the level of carbon in the atmosphere to determine the future temperature increases. The end result is, unless we reduce the CO2 content of the atmosphere, then we are dooming our descendants to possible extinction. But we do have a choice. Right, I'm going back now to our first graph. And the reason I'm going back there was I put all the data up on the board, and it's a bit hard to see some of that data down the bottom there. But I put it into the graph up the top here. So over the left-hand side here, you can see the carbon right up to the end of 2012. So I brought it right up to date. 80 parts per million we put into it in the last 50 years. On the temperature side, we see this starts just below 14 degrees. Notice I haven't used this stupid 0, plus or minus. I've used the actual temperatures. And the reason I've done that is because even that is argued about amongst people. What should be the average temperature? Absolutely stupid argument. We're talking about saving the human race. So that starts just below 14, and it finishes up here at about 0.6 higher. So these graphs show that for every 80 parts per million increase over that 50 years, the average global temperature increased by 0.6 of a degree. Anybody disagree with that? Can you see it up there on the graph? Okay, so if we were to work this out, as I've just shown you, the carbon determines how much the temperature would be. On an annual increase of 0.6 in the temperature, divide that by that 50 years, and we finish up with 0.012 degrees Celsius per year. 0.012 degrees Celsius per year on a linear basis. Or if we'll take 83 years on that reckoning to add just 1 degree of global average temperature. 83 years on a linear basis to add 1 degree of global average temperature. Likewise, if we divide the 80 parts per million on the left-hand graph by 50, we would see that over the last 50 years we have increased the carbon content of the atmosphere by 1.6 part per million CO2 equivalent each year on a linear basis. And by multiplying that 1.6 by 83, we can show that for every 1 degree increase in the global temperature, the carbon content would increase by 133 parts per million. That means for every 133 parts per million CO2 added to the atmosphere, the average global temperature will go up by 1 degree Celsius. And I guarantee it. Maybe not exactly, maybe a few years later, but certainly it'll follow that carbon up in its trend. So we can use that. And if you have a look at this graph here again, on the left-hand side, you can see behind there is a sort of orangey-looking line that goes up to the 80. Over the top is a trend line. That trend line is so accurate compared to the plotting of that graph that we can extend that up to 2100 and see what happens then. Because that's so damn accurate, I guarantee that's as close as you'll ever get using this formula. Because it is not linear graph. In mathematical terms, it's a parabola with vertices down, and we're looking at the right-hand side of it. So we'll follow that up, and if we follow that up to 2100, we'll finish up with 660 parts per million of carbon dioxide in the atmosphere. So I'll show you that. I've already plotted it for you. And there you have your CO2 trend line going up to 2100. Here's your 2100. Plotting that across, you've got your 660 parts per million. If we take that 660 parts per million and divide it by 133, we can find out our temperature increase since 1960, which works out to be 5 degrees. So what I am saying is, if we keep doing what we have been doing over the last 50 years, then the average global temperature will increase by 5 degrees Celsius by 2100. So we're going to be cooking ourselves, add it to the already 14 degrees we had when we started, and add another 4 degrees on top of that, and we've got 21 or 22 degrees average global land temperature in the year 2100. What we've got to try and do is do that. We've got to try and bring that down to the same base we were in 1958. So, we've got to come down here and try our very best to try and come down here and get rid of the carbon. As I said, I don't give a damn what causes it, whether it comes from plants, whether it comes from cars, whether it comes from coal. We've got to get rid of it and bring it down. That's a fact. And I'm not going to argue about the ins and outs of it. If we continue going up on here, we're definitely asking for trouble. That's business as usual. That's the same trend as we've been doing over the last 50 years. And if we carry on doing that, we're going to head for a lot of trouble. In just the last 30 years, China's increased its CO2 content from 1.5 gigatons into the atmosphere to 8 gigatons a year. That's a massive 530% increase in just 30 years for China alone, and they're responsible for the curvature of that graph. Without that, we wouldn't be so high. That's nearly all what China does. You realise they're 23% of the total carbon in the atmosphere. America only 19%. Europe only 13%. So they're the big culprits that have been putting this carbon up into the atmosphere. So it also continues to emit CFCs into the atmosphere, but it wasn't even part of the Montreal Protocol. Therefore, based on these figures, we may expect global average temperature to increase by as much as 4 degrees Celsius by 2100. If the Yanks continue to take it down, if we continue to take it down, if Canada and Europe continue to take it down. But unfortunately, it is likely to rise significantly as India and the other Asian nations which I mentioned comes on stream, and they'll expand their 6%. So there, I think you've seen the worst of this lecture, and I'm sorry to sort of scare you a little bit. I don't really intend to, but I've got sick and tired of listening to all these morons talking about how wonderful it was and it wasn't anything to worry about. Maybe they're helping you not to look at the future and stick your head in the sand, but I'm not one of these people who like to do that. I think if we've got a problem, we need to fix it. And we should do everything we can to try and fix it and try and convince those in power to fix it. So now we have the real picture of the situation, free of politics, free of climate change arguments, and we're able to analyse that real data in real time, which I presented to you today. Having identified the problem and revealed the cause, we can now examine what we can do about it. First, let's have a look at the more common forms of free energy that are in production or just about production ready. I've left out the most radical ideas we normally discuss here at this forum, and all the hydrocarbon using old carbon storage except for one, which I'll talk about shortly. But I've included the hydrocarbon fuels that use energy from the current carbon cycle, which they really don't cause any more of a problem. So let's see what we do have in our arsenal. First, we have hydrogravitation, and that's dam, tide, wave and pumping systems. Secondly, we have solar, which includes solar cells on your roofs, high energy solar, heat exchangers, Stirling engines and hydrogen splitting. Thirdly, we have geothermal, which includes volcanoes and hot rocks. We can, like in Rotorua, they get all their energy from the volcanic system they have there. We won't discuss that because this is old technology, but we will discuss the hot rocks. Fourthly, we have a look at that. That's biofuels and biomass. This is a tremendous subject, and I could spend 2 or 3 lectures just on that alone. Fifthly, we have that's wind, and nuclear is the 6th one. So the wind I'll talk about later in the year, and that's quite a big branch of the subject, as you know. Nuclear fission, of course, that's conventional systems like you have in Japan, like you have in Chernobyl, and they're the systems which they want us to use here as well. Actually, pebble bed's the better idea. It's a little more safer, but not 100%. And lastly, there is nuclear batteries, which NASA's trying to hide from everybody. We should be using those as well, and they sort of kept them out of the conversation for some time, but I'll discuss that later in the year. So let's get rid of those, because we're not going to talk about those today. So first we'll talk about the hydrogravitational. Why I use the word gravitational there, not just hydro, is because most of this energy does come from the gravitation. The water itself is just a medium by which it operates. There are interesting innovations that are already in production that some of you may not already be aware of. So we'll first look at the hydrogravitation and then look at the new innovations in solar and geothermal. First up, we will set the stage with Australia's first non-carbon project.
When the Great Snowy Mountain scheme was finally completed in 1974, almost no one had even heard of global warming. But back then, emission-free renewable energy from falling water provided 20% of Australia's electricity. 30 years later, with climate change a looming reality, hydro's share has fallen to 7%.
I don't know what the future is for hydro storage because I use fresh water for this particular purpose. And controversy over water use, El Niños, increasing erratic precipitation patterns. All this may make it difficult to sustain this type of hydro scheme in the future, but don't worry, there's better systems around. First, we will look at a couple of tidal and wave power systems. This project was started on a Scottish West Coast island about 25 years ago in 1987 as a small oscillating water column project, and that's what OWC stands for. It has proven very successful, and I understand it is still operating. In 2003 they built a new plant of 500 kilowatts which operates also an electric bus around the island because they've got so much power they can't use it now. It has enormous potential along many coastlines for long-term base power as it successfully separates the ravages of the sea from the electrical generation equipment, and that's a big problem with the equipment. It has an automatic clutch drive that uses both directions of wave motion. It can also be designed to be independent of tidal levels. So if we have a look at this little drawing on the right hand side, you can see this mark at the top here, I think you can. That's high tide along there, and that's low tide along here. You can see that this water moves up and down here like a piston, compressing the air that is trapped behind here, forcing it in and out of the turbine. And that's what drives the system. So it's never in contact with the actual sea. It's built on land, so there's no big problem with it. What I would do different with this, I would put a sluice gate down here that you could close when you've got really bad weather that could do the equipment some damage. You can also close it so you can do your maintenance. So that's the only addition I would improve on there. But right now, let somebody else explain it rather than me.
The operating principle of this wave power station is as simple as it is ingenious. An enclosed chamber has an opening beneath sea level, which allows water to flow from the sea to the chamber and back. The water level in the chamber rises and falls with the rhythm of the waves, and air is forced forwards and backwards through the turbine, connected to an upper opening in the chamber. As it is compressed and decompressed, the airflow has sufficient power to drive the Wells turbine. It is a feature of the Wells turbine, named after its inventor, that it is driven in the same direction by both forward and reverse airflow through the turbine. Even relatively low wave motions can generate enough airflow to keep the turbine moving and to generate energy. This is how easily energy can be generated with a wave power station, day and night, all year round, as long as there are waves.
Okay, that's an explanation of that one. So this is also an oscillating water column system, built with investment from the Norwegian government and a leading engineering company, KVAERNER, who normally build oil rigs, so they're generally on the other side of the fence. But they also build natural gas power plants that sequestrate all of the carbon from the natural gas, that's CH4, and produce carbon black as a byproduct, which means it is the only natural hydrocarbon system in the world that has absolutely no carbon footprint. So this is the only one at the whole lot that has no carbon footprint if you're using the KVAERNER process. Australia has huge reserves of natural gas, as you're well aware of. So we don't really need to use coal at all with its 92% carbon, irrespective of whether the government has thrown millions and millions of dollars at it. If you take the carbon out of 92% carbon, what have you got left? Only a few atoms of hydrogen. It's better to use electrolysis and at least get 2/3 of it in hydrogen. What do you want to throw millions of dollars at the coal industry for? Let them start digging a trench across Australia and let's have some precipitation in the middle of Australia instead of digging up coal. It's a pity John Howard sold much of the North Shelf reserves to China for almost nothing. And China doesn't do anything about the carbon about it at all, it just sends it up into the atmosphere. Maybe someone should tell them to use the Kavanagh process. And then they can get some valuable carbon black as well. So getting back to this wave system, it was constructed in 1984 and was destroyed just 4 years later in 1988 by two huge storms. Many wave and tide systems suffer the same fate, or have a very short working life. The sea is just too violent for many of these schemes. This system, however, was rebuilt a little bit later, about 2001 or 2, I think, and it's been working well ever since, so they must have put it in another place, I hope. If we have a look at the cutaway view here, we can see exactly how this operates. The tide comes in here and goes out through this well. The wave motion goes up here and pumps this air up the top here. The amount of wave motion, each wave pumps 1,000 kilowatts of power up here for each single wave, 1,000 kilowatts of power up there. It turns this turbine at 1,500 RPM, and on a regular basis, this little plant puts out 600 kilowatts of power on a continuous basis. Doesn't take much. Cost $1 million to put up wind generator, cost $3.5 million. The Norwegian coast receives about 600 gigawatts of power every hour on average, 600 gigawatts. And that is 24 times the total power consumed by the whole of Australia on an annual basis. 24 times. Imagine what power could be trapped from around our huge coastline if only our government installed the Scottish wave system as demonstrated on the island of Islay. But now we review 3 Australian systems the government is backing, which includes 2 oscillating water column systems and a wave system in Western Australia, plus an independent tidal system that is being sold here commercially.
Mother Nature has been demonstrating her power here for hundreds of years, and her message is finally getting through. This is pure, green, limitless energy, and it's free for the taking. It's an accepted fact that the oceans carry enough potential energy to power every single country on Earth, more than 5,000 times over. But finding an efficient way of harnessing that power has proven very difficult. The problem facing anyone trying to design a wave generator is obvious. Waves aren't the least bit consistent. Their size totally depends on wind and tide. And as we all know, that changes from day to day. But at least one scientist has heard Mother Nature's message. Basing his design on the Kiama blowhole, he's begun an energy revolution. Dr. Tom Dennis is Executive Director of Energetic Australia, and the man who dreamed all this up. A 500-tonne floating wave energy generator that he claims is 10 times more efficient than the best ever built.
See that coming down the line.
This fully operational prototype is moored in Port Kembla, south of Sydney, and is about to be towed into place on the rugged ocean side of the harbour's breakwater.
The device you see out here now is capable, even at this early stage of the technology, of producing enough power for 500 homes.
Working at maximum power, this plant could produce double that amount. That's 1,000 tonnes of greenhouse gas a year that's not going into the atmosphere. There's no disputing that wave power has enormous potential. Back in 1985, Beyond 2000 reporter Ian Finlay toured a Norwegian wave energy experiment that harnessed the rise and fall of passing swells in a huge vertical column. It worked on the basic principle that still applies today. The water level inside this ribbed chamber rises and falls like a giant liquid piston with each passing wave. The compressed air from a rising wave spins a turbine at the top, and as the water drops, the air is sucked back through, again spinning the turbine. The breakthrough with Dr. Dennis's design is that unlike the Norwegian model, it can harness the power of waves even when it's relatively calm.
Well, you can see the turbine operating at the moment just quite slowly because we don't want to put ourselves in any danger, but in real operational mode the blades will be spinning at approximately up to 700 RPM, and the airflow down this passageway here can be as much as 500 kilometres per hour. What we've done is come up with a radically different turbine, and they sense the flow and they react within milliseconds to move to whatever is the best position to extract the most amount of power.
And there's another feature that makes this wave generator so much more effective. These huge parabolic walls either side of the water chamber. They're shaped just like the cave entrance to the KVAERNER blowhole. Seems incredible that no one has thought of this before. It's such a basic solution. Like a satellite dish that concentrates radio waves into a powerful signal, these walls concentrate ocean waves into a powerful force, tripling the energy of a 2-metre swell to that of a 6-metre swell. So even in swells under a metre, power production is still commercially viable. And that's a first in wave energy generation. For the next 12 months, the rig will sit on the ocean floor 200 metres off the Port Kembla coast, being lashed by wind and wave to test its structural stamina and prove equipment reliability. A cable running to shore will add about 1 gigawatt hour of electricity per year to the local grid. Then, if all goes to plan, they'll have critical data proving to the world that their wave power is cheaper than wind power, solar power and even fossil fuel.
Okay, the difference between this OWC system and the Scottish Well system is that in this OWC the blades reverse pitch each time changes direction, which could present, of course, some mechanical problems and give them a fairly high maintenance bill to keep this in operation. I also prefer the shore-based system that is more stable and doesn't require undersea cabling and can be more easily maintained. The wave deflectors are, of course, an excellent idea and act like a carburettor venturi to amplify the energy input. But I wish them all the best, because every little bit of carbon we can get out of there is worthwhile. All right, let's look at another system here.
It's a massive untapped resource that could provide power for the future. And for the first time in Australia, wave energy from the ocean will be trialled at a commercial level. The federal government's putting $10 million into 2 projects in Victoria and South Australia, and Ali Bangari is the chief executive of the green energy company Ocean Link that's behind the trial at Port Macdonnell, east of Adelaide.
Oh, it's essentially extremely important is backing, because we are at the development stage of the technology, and without that sort of support we could not have secured foreign investments or national investments for the balance of fund and develop this technology to a commercial level.
So is it possible that wave energy could in fact provide cheaper power than coal-fired stations?
Essentially that's the aim, and we hope to achieve that aim within 5 to 7 years from now.
So how effective do you think this will be? How much electricity can this system produce?
In terms of production and supplying the essential electricity to households is no different to any other power stations. So generally for every megawatt of power produced, you could feed up to 1,000 homes with that electricity. So this project, for instance, in South Australia alone, is a single unit which got a footprint of 20 metre by 20 metre. Essentially that box at the base of it has got a footprint of 20 metre by 20 metre, and would be able to produce a 1 megawatt, which would feed up to 1,000 homes.
So if this trial works, when do you expect it to be permanently hooked up to the electricity grid?
We expect this to be permanently connected to the grid by the end of next year, 2013. and we're hoping that thereafter we produce continuous electricity onto the grid in South Australia.
Ali Bagai, thanks for joining us.
You're welcome. Thank you very much.
Okay, again, they are using a system that is at the mercy of the sea, and undoubtedly will require a fairly high maintenance bill to keep it going. So now let's look at a slightly different approach in Western Australia.
To help power its Garden Island base, wave energy will be harnessed on a commercial scale to run much of HMAS Stirling. Michael Tetlow has the story.
For the Navy, the ocean is its domain, and within 18 months it'll also be a major source of electricity for the Defence Force at Garden Island. 3 kilometres off the coast, a series of buoys will harness the power of waves.
Certainly by the end of next year, 1 to 2 megawatts of power, which will be the largest wave energy power plant in the world.
The Navy's agreed to buy all the electricity Carnegie Wave Energy can make. A carbon tax battered Prime Minister today praising the plant as the way of the future.
The technology here, making energy out of waves, is Australian invented new technology. It is Australia in the lead.
It's technology that was tested off our coast last year. Buoys pump high pressure water onto Garden Island to run proven, reliable turbines.
We'll have these manufactured off-site, prefabricated, brought to site and then plumbed in on site. But this is 120-year-old technology.
This massive buoy is the one that was used during last year's 2-month trial just off Garden Island. By the end of next year, there'll be 5 of these sitting in the same spot, just a metre below the surface.
Whilst it will vary over time, as you obviously get larger waves some days and smaller waves other days, there's never a day off the southwest coast of Western Australia where you don't have waves.
The electricity this plant will produce could power 500 houses. Kane believes in the future we'll be using wave power from Geraldton to Esperance.
Although this system is designed to avoid the damaging surface waves, it has the added complication of having to pump seawater to the land-based station to operate the turbines. The trial period of only 2 months, so they still have a while to go to prove their long-term viability. But like the other 2 systems, I wish them all the best, because every tonne of carbon we can take out the atmosphere is a good thing. It seems like this system, of course, might turn out to be worthwhile because it's well below the waves, and therefore it's not being subject to the buffeting of the surface waves, so it might turn out to be all right, even though they've had only a 2 months trial. So the last system is a variation of the Bernoulli principle for vertical shaft wind turbines.
Tidal energy, the world's most reliable energy source. Twice a day, and every day since the world began, the oceans produce powerful water currents and tidal movements that are so reliable they can be predicted years in advance. For centuries, mankind has sought to exploit this massive source of potential energy. In Roman times and the Middle Ages, mill wheels driven by flowing water were used extensively for grinding wheat into flour. Until recently, there has been little development in our ability to harness this huge resource of power. Today, the wonders of modern technology have allowed us to extract this huge potential of raw energy for the production of electricity without harming the environment. So why the focus on tidal energy? The world has an increasing insatiable appetite for power. Global warming is compelling us to move away from fossil fuel and other high-risk fuels to clean, green, renewable sources. What are the advantages of tidal energy? It's renewable and sustainable. Seawater is 832 times denser than air, which means an 8-knot tidal current has more energy than a 380 km/h wind. Once a turbine is installed, tidal energy is free. No expensive fuel is required. It has a very low maintenance cost. Tides are predictable many years in advance. There is no impact on the visual amenity as tidal turbine is underwater. It is the most energy dense of any renewable energy source. It produces energy for the lowest cost. According to international environmental expert Dr. David Suzuki, tidal energy has one of the smallest footprints of any renewable energy resource. Experts estimate there is over a staggering 59 terawatts of power available through tidal energy in the United Kingdom alone that remains unutilised. What makes tidal energy different to its competitors? Whilst most companies have been working on new versions of the mill wheel or windmill technology, tidal energy took a different approach, working on turbines mounted in shrouds, also known as venturis, to increase turbine efficiency. In doing this, tidal energy has developed a unique system called the Davidson Hill Venturi turbine that is able to generate electricity from almost any form of moving water. The Davidson Hill Venturi turbine established a world benchmark in 2003 for the highest efficiency ever produced from a water turbine. The unique Davidson Hill turbine achieves the marine equivalent of breaking the sound barrier. Griffith University in Australia and industry experts have independently tested the Davidson Hill Venturi turbine, declaring it the most efficient water turbine technology ever. They also proved the scalability of the design, allowing tidal energy to develop a range of Venturi turbines in sizes from 2.25 metres squared to 100 metres squared, capable of generating power from a few kilowatts to megawatts. The Davidson Hill Venturi turbines can be scaled or arrayed to suit almost any need, from remote settlements to small cities. The electricity produced can be fed directly into the grid or used to offset the cost of existing power generation. It has taken 10 years of intensive research and development, but Tidal Energy Proprietary Limited continues to maintain an industry lead in the development of the most powerful tool for generating electricity from moving water anywhere in the world today. Welcome to the future. Tidal Energy and the Davidson Hill Venturi turbine.
So as you can see, we are well on the way to producing base power that does not rely on nuclear power or coal-fired power station. The sea alone has all the renewable energy we would ever need. And we can look at this in more detail from this map. So this map shows the wave intensity all over the world. As you can see, Australia has the greatest intensity of wave power and could easily satisfy our power needs from tried and tested equipment such as that used in Scotland or the Scottish Islands. If you look along the south coast here of Australia, you can see most of these dots are in the blue. Up the east coast is nearly all red, and along the west coast is nearly all purple. So this means most of the waves striking our southern coast are producing 60 kilowatts of energy for every metre of wavefront. That's absolutely immense, I think. And if you have a look around the world, it's only England and the south coast of South America that has anywhere near that. We're definitely the best in the whole world. We're very, very lucky. Then why the hell aren't we using it? Not 1 watt so far is being produced by anything the government's backed. And I think it's damn well disgusting, because they're spending millions and millions and millions of dollars on wind turbines and not really producing much, only about 2 to 3% of the total need. If they spent that money on introducing wave systems instead, we'd be producing most of the energy for Australia that would need a very, very short period of time. And we wouldn't need to waste any on running coals. And even if we didn't do that, if we used our natural gas reserves, they're going to last another 200 or 300 years, and we use the KVAERNER system, we still wouldn't put out a single gram of carbon into the atmosphere. But thank you, Mr. Howard, for what you did for us. Okay, so now let's have a look at hydro pumping storage as one of the best long-term systems for storing base load power. So that's what we're looking now at, is storing the electricity for intermittent schemes. Obviously we can't do this with lead acid batteries because the cost would be phenomenal, but we need some other scheme to be able to store that. So this type of energy storage is not restricted to using fresh water. Like normal hydro schemes depend on precipitation. Many wind farms are located on high ground along the coast or offshore near cliffs, so that wind turbines or wave or tide systems can be used to pump seawater up to an elevated coastal line reserve. And that reserve can then be used to provide base load power whenever it's needed. So if we have a little look at this, it can also be used inland. So you don't need to have a very big storage system here, just something 40 metres up in the air. So if you've got a couple of hills about 40 metres up, you can put a fairly small system up here that probably lasts about 4 or 5 days of requirements. When it gets pumped down here again, you've got another one down the bottom here, so you can use this for inland, for your solar systems. You can also use it for your internal wind systems. So when you've got wind or when you've got sun, they pump the water up to the top, and when you need the base power, down it comes again. Of course, on the coast, you don't need this bottom one at all. They just use the seawater, pump the seawater up. And it wouldn't take long for a small reservoir up here to be filled by precipitation. Once it's full, of course, you've got it continuously, up and down with the pumping. The only thing to waste it, of course, is evaporation. And you might get enough precipitation to be able to fill it on a regular basis without having to worry about refilling it by other means. So the last hydrogravitational scheme we will now look at is extremely revolutionary and based similarly on this device. But its initial cost will be immense, and I don't know as we need it here because we've got too much wave power, but certainly the Scandinavians can use it. So we spend billions on building bridges and tunnels all over the world, and the number of these projects have involved reclaiming the sea by the construction of artificial islands. And of course nobody's better at that and doing it than the Dutch and the Scandinavians. So we already have the technology to accomplish this project, which is expected to get the go-ahead sometime this year. The island can be made from the sand dug out of the hole and will provide space for 500 megawatts of wind turbines on the embankment. Other forms of energy are also possible, such as biomass and tidal around the fringe. It is one of the most ambitious clean energy projects ever conceived. Once completed and provided it is able to withstand the North Shore storms, it should be able to provide free, clean energy indefinitely without any environmental impact and without any maintenance costs involved. As you can see here, it's 6 kilometres wide and 10 kilometres long. And all around the edge here, you can probably see, just make out wind turbines. And if we go to this bottom drawing here, you can see these are where all the pumps are, and as long as these wind turbines are operating, they pump all the water out of the hole here, which is 40 metres deep, and provides up to 30 gigawatts of power. When they need that power on the mainland, they treat it like any snowy mountain type scheme. Down it comes down the raceway, hits the hydroelectric turbines and generates electricity for the mainland. They're not restricted to making one of these, they can make heaps of them, and that'll produce energy for all the Scandinavian countries without having to worry about all these windmills on land and wasting their land area. So they can certainly do that on the sea. And now move on directly to solar energy to look at the new innovative schemes now being installed across the world. Some of these schemes also carry their own energy storage systems to allow them to be classified as base load electrical supply systems. So the first one we'll look at is a high energy solar scheme and was established here in Victoria.
There's another plentiful renewable resource in Australia's vast outback. Not wind, nor hot rocks, but sun. In the view of its enthusiasts, solar power can save the world and the Australian economy too.
When you look on a global scale, this is really the big one. China has huge deserts, and it is the biggest single Chinese resource potentially. India has huge deserts. The United States has huge deserts. These are the major carbon emitters in the world.
It's an economic opportunity. We have a plan to be a part of a growing and very vibrant, and as we're now seeing, extremely exciting world market.
In the red heart of Australia, 3 remote Aboriginal communities draw power from the sun. This is a pilot station for what its makers claim could be the solar technology of the future.
We buy lots of cheap glass by way of mirrors, and we concentrate it about 500 times. And we literally take light and convert it directly into electricity with very, very efficient photovoltaic technology.
The photovoltaic cells at the heart of the system are at the global cutting edge. Originally developed to power satellites in space, they're the result of a collaboration between the mighty Boeing Corporation and a small private company with an office and workshop in a back lane in the Melbourne suburb of Hawthorne.
A solar panel that you'd see on the roof of a house is about 2/3 of a square metre and maybe 80 to 100 watts. This is one of our solar panels and it's about 550 watts. So you can see the difference in area. It's about 1,500 times more effective than a normal solar panel.
Okay, as I'm sure most of you know, this scheme is operating out of the little desert in Mildura, and you've probably seen it on the news. I recently ran into financial trouble, but I believe that has now been sorted out. That's the trouble setting yourself up in Australia. Just how advanced they are now, I don't really know, or whether the federal or state government intend to build any more. But let's hope they do better in the future. But as I said, we need every little bit of carbon we can get out of the atmosphere. So now let's have a look at an American solar heat exchange system that has just recently started up in Nevada. Huge system.
Now, in the Nevada desert, a few miles from Las Vegas, a 64 megawatt solar thermal power station is nearing completion. Apart from those in California, the biggest in the world. Compared with solar systems' advanced photovoltaics, parabolic trough technology is simple. It depends not on the sun's light, but on its heat. Until the plant's completed, its long rows of mirrors are turned towards the ground. But in a couple of weeks from now, they'll start tracking the sun.
As the sun's coming up over here in the east, the parabolic structure moves like this, so it's always tracking the sun. The glass reflector panels here reflect about 92% of the light that hits them onto this receiver tube here, concentrates about 70 times. So there's 70 suns on this receiver tube that heat the fluid that we use up to 390 degrees. That then goes back to the power plant to a heat exchanger, makes steam, and the steam generates power going through a steam turbine generator, very traditional to most power plants throughout the world.
Parabolic trough technology is tried and tested, but at present it's far from cheap. What makes it economically viable in Nevada is that its output matches demand.
Well, as you said in the article there, this technology is not new. As a matter of fact, it's about 50 years old. The Americans built a large similar plant to this one in the California desert about 20 years ago when the price of oil went up. But when the price went down again, they put this big plant in California into mothballs. But with this new threat to the environment and the lucrative government subsidies the Americans are now paying, these plants are being rolled out all over America in all the desert states. We'll now look at the world's most ambitious solar boiler system in Spain, and probably some of you have probably already seen this one.
From the distance, it doesn't seem real. A strange tower, 40 stories high, bathed in light. But this weird new landmark in a field outside Seville is actually a new kind of solar power station. Some civilizations worship the sun, here they harness it. And these beams lighting up the sky could help head off the worst effects of global warming. When you're close up, these look just like steel panels, but in fact, I'm standing in a field of giant mirrors, all focusing the sun's rays in one direction. The beams are aimed at the top of the tower. It's painful to look at, but it's here that the sunlight is transformed into thermal energy. All of this sunlight is reflected up here to the top of this tower. It's incredibly bright and hot. The temperature here can reach more than 400 degrees centigrade, enough to power a boiler here, which in turn goes on to generate huge amounts of electricity. The steam created drives turbines, just like in a normal power station, and the heat can be stored in these tanks, so even at night the system can generate power. Each mirror, and there are 600 of them, is adjusted to generate the right amount of heat. In the control room, they keep watch over a power station that amazingly gives off no greenhouse gases. The biggest challenge, keeping the mirrors clean. But what about the costs? Well, power from here is 3 times more expensive than from a conventional power station. But this is the first of its kind.
I am sure that in the course of the next 5 years, we will see similar cost reductions in this technology as we have experienced with wind and other technologies.
And there are plans for a huge expansion. Already fields are being prepared for thousands more mirrors. Imagine installing millions across the Sahara Desert and sending the power north to Europe. That is being considered.
Okay, this system is fairly rudimentary, as you can see, and the hardware is easy to install. It clearly does the job and also provides base power, which most of the other solar systems don't. It does seem efficient and easy to maintain and could quickly be installed in many of the equatorial countries around the world. So that means the Asians can put this up and save us putting a little bit of extra carbon into the atmosphere as they come on stream as well. So that's an ideal system for them. This is a plant you've been looking at over here, and this is the tower. This is their original pilot plant that they used before they built the second one, and you can see how big this other one is. This is over 1,000 mirrors on this particular plant, 600 on this one, and over 1,000 on this. The last solar device I will show you now is one of my favourites and was designed by Roy McAllister in the US. It is based on the Stirling engine, and I think it has tremendous potential in many, many countries across the world.
We have a solar furnace 90 million miles away that provides life for all of Earth. In the past, we've been unable to harness that potential because the efficiency, the cost, etc. of the system just didn't make it viable. What's changed is technology. The technology now allows us to build large-scale, highly efficient, cost-effective systems.
Each dish tracks the movement of the sun across the sky, focusing the heat onto a single point, where it is converted to electricity. They are twice as efficient as any other solar power system. With one, you could power a small village. A field of them could power a city.
Each system produces about 25 kilowatts, which is enough to power about 10 homes. However, we plan to deploy these on a large scale, 20,000 of these, which is massive, about 500 megawatts, which is the equivalent to a coal-fired plant or maybe even a nuclear plant.
The ink is just drying on the contract to build the first commercial solar power station. It will fill 5 square miles of the vast Californian desert with mirrors and will supply electricity to the city of San Diego. In time, as the technology and efficiency improves, systems like these may spread around the world.
Okay, Roy McAllister has also developed a number of other alternative energy systems based on conventional technology. He has developed an efficient biodiesel system for use in cars and a hydrogen generating system that can be used in conjunction with this Stirling engine for base powers. A few years ago there was an article on TV about the development of a solar cell called Slither technology, and it was developed here in Melbourne. It was claimed to be 10 times more efficient than the conventional solar panels, which was demonstrated in the article we saw on television. Ian found out that Origin had bought this technology and moved it to Adelaide, and we haven't heard a word about it since, have we? And so I wish they'd get off their cart, because if this is 10 times better, as they showed in the article, they showed one panel. What they did was take a BP cell, which is about that size, a little bit smaller, on a solar panel. Let's cut it up in slithers and stuck it on a base and then wired it up, and they found each slither produced almost as much power as this whole BP round cell which you stick on your roof. So why should you have 24 or 25 or even 48 panels on your roof to try and generate 3,000 or 4,000 watts of power when you can have just 2 or 3 of these particular cells to do it? So I wish Origin would get off their bums and start introducing this commercially, then a lot more people would have these solar panels on their roof, because you'd only need 2 or 3 of them to produce the same amount of power. All right, let's move along a little bit from here. So now we're going to have a look at geothermal, and as I said, we won't worry about volcano because that's old technology. So we now finish off by looking at one of the geothermal systems that are being trialled here in South Australia. And I had a lot of hope for this to start with, but that's waned a little bit recently.
Through 3.5 kilometres of sedimentary clay and shale that acts like a vast insulating blanket. Beneath the sediment is a layer of mildly radioactive granite, several kilometres deep. For eons, the heat produced by its radioactive decay has had nowhere to go.
We're looking at 3,500 metres down at the hottest rocks on Earth, outside volcanic regions. And that's quite special because temperature, apart from giving us more energy, gives us a huge increase in the efficiency with which we can convert that energy into electricity.
When the drill bit reached the granite, geodynamics chief scientist Dr. Doon Wyborn got a surprise. He'd expected hot, dry rock. What he found stored in fractures in the granite was water under colossal pressure.
We've been monitoring the pressure in this wellhead for a number of years now, and it's an incredibly high pressure. Here, the pressure is actually high enough to force the water 3.5 kilometres up into the air.
3.5 kilometres?
3.5 kilometres.
Geodynamics' plan is simple enough in principle. Water will be pumped down injection wells through the overlying sediment and into the granite beneath. From there, it will seep through natural fractures in the rock, which will heat it to 250 degrees. The superheated water, still under pressure, will return to the surface via production wells and pass through a heat exchanger before being pumped back underground in a closed loop. From the heat exchanger, a second closed loop of fluid will heat steam to drive a turbine and generate electricity, potentially a lot of it.
We're looking at hundreds of megawatts into the grid by 2015. And that's just this company. Other companies are looking to do the same. By 2020, there will be several thousand megawatts going into the grid.
Okay, I was told recently that geodynamics had some trouble pumping the water down the hole. When the water spreads out in the sedimentary rock at the bottom of the well, which is about 3 kilometres down, it tends to break down the surrounding rock formation instead of spreading out through the cracks in the rock. This may prove to be a major problem that could prevent this project from being viable over the long term. However, I believe there's a few of these systems already in full production, one in New Zealand and I think another one in South America, and there's also one in Queensland which I don't know anything about. So it may still prove to be quite a winner for base power as a substitute for coal. Unfortunately, geodynamics has had some very, very bad luck. When drilling their first production hole, drill rods were dropped down the hole after the drilling was finished. And don't forget, this is 3 kilometres down, which may or may not have been sabotage, and I'm not real sure whether it was or not. They tried to hire another rig from a local petroleum company, but were refused. So they had to buy their own from Texas, which set their project back nearly another year. I was going to try to go out there last year when I went out to South Australia, but didn't make it, unfortunately. I hope to go out there sometime next year and see how they're coming along. All right, well, we're just about finished on the geothermal side. So now we'll have a look at the biofuels and biomass systems. I won't spend too much time on this. However, interesting research has been carried out in Australia in developing algae, grown on large shallow ponds as an energy source, which I think I better discuss before we finish off tonight. So Dr. Joanne Quinn of Flinders University investigated the use of this well-studied green algae known as Botryococcus bruni, or BB for short. BB is colonial algae that flourishes in brackish water, lakes and reservoirs, where it blooms into large green floating mats, and up to now there's been a real trouble on some of the waterways and around the coasts where there are swampy areas. Up to 75% of the dry weight of this particular species is a biological hydrocarbon that can be converted into petrol, diesel or other liquid and gaseous fuels. This project, like many of the other systems we have examined here today, has huge potential. It can be installed in salt water marsh areas or use made of seawater ponds around the coast on unusable land. It doesn't need precious fresh water or use valuable fertile farmland. At the same time, it is an excellent carbon sink that can be used time and time again without any detrimental environmental impact. So you could fire your car on this one and you won't have to worry about it at all. I feel guilty about putting carbon into the atmosphere. As I said, this is a bit of a big subject, so I just put a few of them there up on the board, and I won't discuss many of those. So this chart demonstrates the various processes used to turn crops and biomass waste into usable hydrocarbon or heat to drive machinery. For our investigation, the most important of these are biofuels such as methanol, ethanol and biodiesel. The production of most biofuels are well-established processes using recycled carbon and therefore do not present an environmental problem. As time goes on, many of these variants of fuels will replace fossil fuels or blended in with fossil fuels to reduce the carbon footprint. However, the use of corn as a raw material for the production of ethanol has been financially encouraged in the USA. This is a very dubious practice, as the amount of energy input into growing the corn is similar or possibly greater than the amount of ethanol produced. And of course the corn is diverted from human consumption. So if you finish with that, I'll move on to it, so I won't go into those. As I said, it's rather long and involved. Collectively, there are approximately 140 biomass processing installations in Australia. These sites recycle consumed carbon and therefore do not increase the total carbon content in the carbon cycle. The main opposition is like the previous one. These processes, if they use good farming land, fresh water and carbon polluting machinery are used to produce this material, then I think it's very bad. In my opinion, the use of the saltwater algae, as we looked at first, seems to me to be a far better approach than using good farmland for producing ethanol. If we go over to this graph here, we see that in Australia we are producing about 1 gigawatt of power from the various plants we have. There are about 35 biomass plants here in the sugar refinery industry where they use their waste to run their own machinery, and say actually not about environmental, they're just saving themselves a bit of electricity by using their own waste. And the same is true is of course of the wood chip industry. What really upsets me is there's only 17 methane biomass sites in sewerages, and the same for landfill. There's only 57 of them. There should be hundreds of them here, and we should pass some legislation to ensure that all these plants are using methane capture and then putting it onto the grid. And the same true, of course, for the landfill sites. There should be hundreds of those. So instead of just 1 gigawatt here, we should have about 50 to 100 gigawatts being produced by this and using the methane in a worthwhile way instead of just wasting it up into the atmosphere. And as I said before, that's 20 times more effective at blocking infrared radiation than CO2. So we need to be able to use it efficiently. The sheer number of alternative systems that either use non-carbon sources or carbon sources that is already in circulation indicates that we really do have the solutions. We can do without coal and petrol to power our machinery and still live the life we are accustomed to. So there's no need to argue about the modelling or to hide your head in the sand, because it is easily doable. Once we establish non-carbon based total electricity supply for reticulated sources or from holistic plants as on farms and places like that, then electric cars, biofuels and fuel cell vehicles and hydrogen powered engines for rail and air transport will complete the changeover. So what's the big deal? No new technology is necessary. All we have to do is convince the big energy consortiums that we all share the same lifeboat. And what happens to us also happens to them. Thank you very much for listening to me, and I hope it has been informative for you all. Thank you.